So, I was supposed to talk about the bounded Farrell-Jones assembly. And I'm reverting the order because there's nothing called the bounded Farrell-Jones assembly as far as I know. So I don't exactly know why it was referred to because it doesn't make any sense. But let me tell you what assembly is. And let me take you back to the late 60s when assembly was introduced. Last century. So who introduced assembly? How was it introduced and who did it? It was introduced by Frank Quinn. And what Quinn did was something rather unusual. Surgery theory had just been developed by Browder, Novikov, Sullivan, Wall. And Wall had actually sort of done the last bit of surgery theory. And then Quinn constructed a functor from spaces to spectra. Well, let's say from spaces to spaces. L of x is an infinite loop space. So those of you who know what a spectrum is, it's better to think of it as a spectrum, but you don't have to. With the property that pi I of Lx is the ice wall group of the group ring of the fundamental group of X. And you have to remember that this is before algebraic K-theory had been invented. It is before K-theory had been invented. It's before A-theory had been invented. I mean, nowadays we're so used to the notion that we take a space and we construct a spectrum and we take the homotopy groups and that's how we define things, right? But these groups were already defined. So in some sense it was really very, very strange that he constructed a space whose homotopy groups were the groups we already knew. But he did. Then if you have a finite complex K, and let me take a finite complex that we all know and love, namely the circle. You can build the circle if you have a Lego set. You can make these 4 blocks long and the corners 2 blocks long. And now you see why it's called assembly. Because you can take these 4 pieces and put them together in the corner. You can assemble them to something which is like a circle. So to get from this to that, it's assembling. That's not what we call assembly. That's not quite the reason it's called assembly. But it's a little bit like that. But what Quinn did back then, he took the disjoint union of simplexes in K. And then he took the disjoint union of L of those simplexes, K, modulo gluing them together the way K is glued together. And then he mapped that into L of K, because everything is compatible with everything. And the way you glue together, of course, I mean, if I'm supposed to be completely honest, it's not just the spaces. You have to do some of you are used to, when you say homology, I mean singular homology, if you want to do this with spectra, you say X smash a spectrum, and then you take the homotopy groups, that's a limit. It's the same phenomenon here. So this is the assembly map, because you're assembling things. And what do you have on the left-hand side if you take the homotopy groups? You have Hi of X with coefficients in the L spectrum. And on the right-hand side, you have Li of Z pi 1 of K. So in other words, what you're doing is you're trying to force excision on this functor. You can also see that that on the left-hand side, I mean, another way of thinking of it is to say that on the left-hand side, you can't really move here, right? So you have control. On the left-hand side, you are controlling things, whereas on the right-hand side, you're free to move all the way around, right? Here you haven't put things together. So this is the reason for the word assembly, that it was done this particular way. And of course, I mean, later on, the very same method was whenever somebody invented a function of this type, they could do the same game, and they did. But actually, Quinn did a little more, and okay, it was a little bit controversial because there were some small problems with this. I mean, they were problems of a nature that we certainly easily can solve today. I mean, they weren't bad problems. There was something about low dimensions. There was some confusion. He turned the spectra upside down. I mean, there were lots of small things, but I mean, it's not something that really should disturb you, and we can certainly easily solve it today. Then he made another kind of assembly, which is sort of a little more impressive, actually. I don't know that he used it for anything, but he made this kind of assembly. If you have a map from Y to K, then you look at your K as a disjoint union. No, look at, what am I trying to say? You write as a union of simplices. Because K is triangulated, let's call this map P. And you look at the union of these P inverse of sigma. So this way you're introducing a local fundamental group, right? I mean, you have a simplex downstairs, but the inverse image could easily have a fundamental group. And then what he did was he said, take L of P inverse sigma and glue it together the way the things were glued together before. So technically nowadays you'd call it a Hoch-Cold M, but it doesn't matter. I mean, I'm just trying to convey the idea here. And then you map that into L of Y. So that's sort of a generalized assembly map where you allow the local fundamental groups you're parameterizing by the simplicial complex K, but you're allowing the local fundamental group to vary as you move across. To the best of my knowledge, this example contains all examples of assembly maps that we know today. And more. I mean, it even contains some that we're not interested in at all. Because, I mean, you could do this for the hop vibration, right? The Witten hop vibration, S3 down to S2. And you'd get something where you have non-simply connected stuff on the left-hand side and simply connected stuff on the right-hand side. That's not something anybody has studied, as far as I know. Okay. So this was how assembly was introduced into mathematics. And of course, that's the special case where you go from hi of B gamma L of 1 to Li of Z gamma. And that's often the one that people called the assembly map. And one way of thinking of that is to take the example on the right-hand board here and go down to B gamma. Because the inverse image of every simplex will just be a contractible space. So the L theory you get out of each of those. So this is, for all practical purposes, this is the identity. So you're just getting what you had here. Now what Farrell and Jones did was they wrote E virtually cyclic gamma cross gamma E gamma down to E virtually cyclic gamma mod gamma. And the Farrell-Jones assembly map is this one. And of course, you have all kinds of possibilities of varying what you put in here, right? But this one is the one that that Farrell and Jones constructed. So it was constructed out of the original ideas from Quinn. And of course they did it both for K and L theory, because in the meantime Quillen had constructed a functor that gives you algebraic K theory. There are technical problems here and there, but nevertheless he had. So let's see, I'm trying to do this fast. So now I've explained assembly and I've explained Farrell-Jones. Now I'm missing to explain bounded. So why do we say Z gamma here? Why is it the group ring that occurs in surgery theory? The reason it's the group ring that occurs in surgery theory, what you're trying to produce a homotopy equivalence. You have a map from a manifold to a quadriduality space, and you want to change it so it becomes a homotopy equivalence. But then that means you have to have an algebraic test for homotopy equivalence. And the algebraic test is given by chain complexes of Z gamma modulus. That's why it's Z gamma that occurs there. Now I want to say bounded. So I want to take a metric space E. And I want E to be a proper metric space, meaning that balls are compact. And I think I can say this rather generally, but you can think of E as being the reals or Rn or some kind of, maybe even some kind of E gamma where B gamma is finite. But you can actually think of E as being anything. It works no matter what you're talking about. So what's the test? What's the algebraic test of a bounded homotopy equivalence to something, say homotopy equivalent to E? E may be a manifold, and you're asking for an algebraic test. So what I'm aiming for when I say bounded theory, I'm aiming for something where I have on the right-hand side, I want to have an algebraic test for bounded homotopy equivalence. And on the left-hand side, I want to have something that's excisive, right? And looks like it when you put in a point, say. So let's try and see if we can do that. So I need to find, so here, you're talking about the category of finitely generated free C gamma modules and morphisms, and I need to find something that fits with this one. But that's not so hard, but I'm going to do it in a slightly complicated way. So let's take E here. And let's take and cross with 0, 1. So I'm looking at E cross a half-open interval. And now I'm given that space here, I want to construct a category. So the objects are going to be, let's just say free C modules. I'll leave it to you. If you wish, you can replace Z by something else, right? But you can work with just free abelian groups. And at points in this space here, I'm going to put free C modules in such a fashion that for every compact space of this space, I only have finitely many, but infinitely many altogether, which means I can come very close to 1. What's that? Many points, and at each point I have a free abelian group. Okay, and that's going to be an object in the category. Now I want to do morphisms. Well, morphisms are just going to be, there's going to be a morphism from the module sitting here to a morphism sitting some other place. And the condition I want to put on them is that for every morphism there's supposed to be some k, so that if the distance is bigger than k, that morphism is 0. This ensures that you can compose these morphisms. I want to have a little more condition. I want to say that so arrows longer than k are 0. I also want to say for every level here, there has to be a level here so that morphisms don't go in between here and here. And similarly over at 0, I want to say that for every level here, there's a level here, so that the morphisms from here to here don't. They're 0, yeah. What's that? Yeah, but I don't want to. Yeah. But it would be the same as stretching out the interval to 0 to infinity, that's correct. They mostly go vertically, right? But they're allowed a bounded amount. Now, here, this category is not so interesting. The reason is that this is a category, and you can take its K-theory. You can restrict to the isomorphisms and take the K-theory is 0. Or you can take the L-theory. I mean, you have to get some involution on. You can take the L-theory, but the L-theory is 0. So, see, for bad reasons, I called this category C way back when. So we don't do that. We have to get something where you don't get 0. So what we do is we take a germ category. We identify morphisms if they only disagree. If they only disagree in some neighborhood of 0. So in other words, if two morphisms are equal in a neighborhood of 1, you identify them. Now you have a category that can test bounded homotopy equivalence. It's actually a D-loop of the most natural category that can do that kind of test. But in a second, I'll tell you why I do a D-loop. The reason that's because I want to do a bounded assembly. So I want to have another category here with the same objects, and the morphisms have to satisfy the same conditions and some more conditions. And the extra conditions is so remember they live, 1 is not a part here. They live between 0 and 1. So here you want to have continuous control at points here. So you want to say that for every neighborhood, there's a smaller neighborhood, so that arrows going here are 0. In other words, the length of the non-zero arrows becomes small as you approach 1. And of course, that's included in here, right? Small ones are included. And once again, you take germs near 1. Now, if you study what is, say, what is the K-theory of these categories? The left-hand side will be homology with locally finite coefficients of E in the spectrum K of Z. And the right-hand side will be, bounded K-theory, I don't know, K-theory of C of E D-looped. So that's an assembly map. So this fits into, if you want to study, if you want to do surgery theory, so I should write L, if I write L instead of K. If I want to create a surgery theory where I want to test whether a certain map between manifolds is a bounded homotopy equivalence, meaning that it's a homotopy equivalence and the tracks of the homotopy have a uniform bound measured in some kind of metric space, E in this case. But of course, if I had more time, I would have said that you could also have a map from the manifold to E, and you can do all kinds of stuff like that. But this gives you a bounded surgery theory in which this plays the role of the assembly map. And if, say, so an example, if E is Rn, then this is an isomorphism. That means that the bounded structure set of Rn is a point. Well, that implies Kirby-Siepman's annulus theorem, and it applies Siepman's approximation theorem very easily. Another thing, just to relate this to what Gulyang was saying, if this is a homotopy, if this is an isomorphism on these groups here, you can do this so that you get a group action on these spectra here. And the fixed set will then be the usual assembly map for E mod gamma. And you can use that to prove that the standard assembly map is a split monomorphism. But I think I'll stop here to give us a break. Yeah, you can see. Yeah, you very, in this picture you see very quickly. And it's kind of interesting, because they're small here, you have complete excision. And to all the C-star algebras in the audience, a lot of this stuff is extremely similar to what Kasparov did in KK theory. And you get the same kind of stuff. I mean, you get, just like KK theory has unbelievable excision, you get that here as well. You get excision with respect to any closed subset. So you get a Steenrod homology theory, if you happen to know what that is. And that's also what Kasparov gets. He gets a Steenrod homology theory.